All right, you guys hear me? All right, well, I can't tell if anyone's in here or anyone can hear me. So if you guys can hear me, why don't you guys say something in the chat? Just say hi or anything like that. Again, I don't think I've actually done live YouTube lectures here, so plus I'm trying something a little different, so. Oh no. I realized I just started this stream with normal latency, so there's going to be a little bit of a lag here. I was having trouble getting this started, so I wasn't sure, so I messed around with settings. All right, good. So you guys can hear me? All right. Well, so let me just say a couple things first before we get started. Um, the the final exam, as we know, okay, so it's going to be at our regular time, which someone feel free to correct me if I'm wrong, is going to be 1:30 on Monday. So the way it's going to work is at 1:30 sharp, I'm going to post to Canvas the the final exam. And the way it's going to work is that you will be able to open up Canvas and look at it. You don't need to print it out, but you will need the same number of pages in blank sheets of paper. So if my final exam is 10 pages, you need 10 blank sheets of paper. Okay? And what you'll do is just like with this sample, this practice assignment for scanning, you will just write your name in the sort of position where the box should be on the front page and then put it aside. And then you will just do one question per page. And I would write question one at the top of each page so that I can tell that it's question one, so that it matches up. Okay. And then when you go to submit it, you just use Dropbox or whatever to scan, and then you just scan scan it in the correct order. It's really important, and then submit it via Gradescope. So hopefully you guys have all looked at the Canvas page and given that a shot. Why do I only have 12 viewers, guys? Let's get more viewers here. Tell your friends in this class that they should log in here. Anyway, so I noticed my practice scanning assignment did not have a lot of submissions. So there's about 50 people in the class. I don't know how many people are still haven't just given up. So I don't know how many people are actually actively participating in the class currently, but only 22 people have done the scanning assignment, and I want to get that to as many people as possible. I want to have everyone get that worked out by before Monday, basically. Before the final goes, I want everyone to understand how they can scan a document and upload it to Gradescope. Okay, so it's really important that you guys give that a try. All right, and so let's see what else I have. So, are there any questions? Have you guys had any trouble with the Gradescope assignment? Yeah, just if you're just tuning in, apologies. There's going to be more lag on this stream than I intended. I screwed up the settings when I started it. So, is my voice sound fine? Everything sounds good? It's an appropriate volume. It's not too quiet, anything? So, yeah, so if you're in the chat right now, please feel free to ask questions, guys. I don't have a lot to talk about the final. It's going to be, I'm going to give a final roughly the same as I might have if it was in class. I'm not going to do any questions in there that are purely computational. What I mean by that is I'm not going to just say find the reduced echelon form of the matrix, because if I said find the reduced echelon form of the matrix, you can just get out a matrix calculator and have it do it for you. What's the point? So you know, like you might need to find the reduced echelon form of a matrix, but it'll just be a part of a problem. Like if I ask you, like, just to give you an example, are these three, are these like four vectors linearly independent? And if you have to, you know, plug those into a matrix, make them the columns of a matrix, and then do row operations, that's fine. It's just that it's not going to be purely computational. There's still a thing you have to understand about that problem, right? So the computational part of that problem will be, the weight of that will be pretty low, I think. Ivania, yes, you can print the exam. It's just going to be a PDF link, so you'll be able to get it and print it out if you want. It's no problem. That would actually be fantastic if you did that, by the way. I would really appreciate it. If you can print it out, yeah, please do, but I just don't want to have any... I don't want anyone to worry that they have to print it out. So you don't have to print it out. You can just use blank sheets of paper, but I said just... You should essentially pretend that you printed it out on your blank sheets of paper, right? Write everything where it's supposed to go on the appropriate sheet of paper. It might help you if you have a stapler to just staple it to begin with while you're working on it, and then you can just write problem 1, problem 2, problem 3 on each page. And then when you're done, you need to scan it. You can just take out the stapler. You don't even really need to. Unstaple it. So just. Sorry, can you go over the second question in the final sample exam? I will be happy to. Just give me a minute. I want to answer questions about the final first really quick, but I'll be happy to do that for you in just a moment. Is the final going to be recently covered topics or a balance of all topics? So, hard to say. I guess I would say that stuff since midterm 2 will be disproportionately, there'll be more of it. So, stuff since midterm 2 will be more representative on the final. So, I don't know in what ratio, but since you haven't really been tested on, you know, diagonalization, eigenvalues, eigenvectors, orthogonality, there's going to be more problems about that than there will be other stuff. So what the ratio is, I don't know. I mean, it's about a third of the class. Maybe it'll be half of the exam to maybe even 3/4 of the exam. I guess if you need to focus on something since your exam's in 2 days, yeah, focus on the newer stuff. That being said, the newer stuff's pretty simple, right? Like diagonalizing a matrix, you should be able to do that. Like it's mostly just the computations that you have to worry about. Okay. The second question in the sample final. Yeah, give me a moment here to just pull it up. Oh wait, that's not what I want. Okay. To show it's orthogonal, right? For A, so sorry, I got hair from my iPad here. So for 2A over here, or on the sample final. So Wesley, I can't really stop you, right? Like, I guess I could demand to see the row operations. I mean, I don't know. I just I'm going to say no. I'm going to say no, you're not allowed to use a calculator. And the only way I can really enforce that is I'm going to need to see row operations, right? If I only see if I see here's a matrix A and now here's its reduced echelon form down here, you know, then you're not going to get points for that, you're not going to get points for doing it correctly. I mean, I might give you points for the concepts correctly. As I said, in no problem, I'm not going to ask you a problem where I just say find the reduced echelon form of this matrix. Like that won't be the whole problem. You might have to compute a reduced echelon form in the process of solving. But I guess my point is, if I do put that in there, you should show the work. Otherwise, I'll probably deduct you some points for not showing work. Now, you can use it to check your work because there's literally no way I have to check that you're not doing that. So basically, if you have some calculations in this test, you need to show your work. All right, I'm going to do 2A. Feel free to put some more questions in the chat, and then I can go through them in order. So 2A for the sample final. Okay. We have B is this matrix, and we have V1, V2, and V3. So it says show that B is an orthogonal set. So for that, you just take V1 dot V2, V2 dot V3, v3, and v1 dot v3. And you compute those dot products. Now, I believe, let me check really fast here. I don't know if I posted it in, I don't know if I made an announcement on Canvas, but I definitely posted the solutions to these problems in the files section. Yeah, so you can go to the file section if you want solutions. I don't know if I said, I don't know if I made a, if I don't know if I linked them in the Canvas announcement with the sample practice final, but you can definitely get the solutions in the file section. So I'm not going to go through these individual, dot products here, but I'll just let you know, compute the dot products. As far as the set being orthonormal, we did not discuss orthonormality in our class. All that means, though, is that it's orthogonal and they're all unit vectors. So it's definitely not orthonormal because none of those vectors are unit vectors. But you don't need to know the word orthonormal, but it's not super hard. Let me go through the rest of this problem. Find the nearest point denoted B hat in the subspace W spanned to B. Don't worry about that one. That's not something we covered. What is the distance between B and W? I guess. All right. So, all right. I clearly did not read this carefully enough. So for 2A is what you need to know. B through E, don't worry about it. So sorry, B through E is not tested for us. Okay. I clearly needed to read this more carefully. Sorry. In regards to quizzes, Matt, I don't know. Nobody emailed me to say. I guess maybe if I said I would do it, then people maybe just didn't go to discussion section. So I guess I'll probably end up dropping 2. No one emailed me to ask, oh, I've already missed 1. Can I get another one dropped or anything like that? So I feel like, I don't know, did anyone skip 1 or did anyone stay home sick because they thought I said that I was gonna drop 2? I don't know. I guess if I said I dropped 2, I should probably just drop 2 then. So I will drop 2 quizzes officially. That being said, a thing that maybe some of you are not going to like to hear, some of you won't mind, some of you probably will not like this. The final exam is probably going to have to be a lower portion of your grade. So they gave me the permission, the math department gave everyone permission to lower the percentage of the final exam in the overall grading. And I think right now we're at like 40%, right? Our final exam is 40%. While I'm talking, please, if you have more questions, feel free to ask. Let's see. Yeah, the final exam is 40. I haven't decided how to sort of what I should make it, but I know a lot of they sort of suggested since since there's more sort of possibility of cheating with an at-home exam, I know it was essentially suggested that we should lower our percentage of the final in the overall grade. So I don't know how I would do that. I would probably drop it down to like 30 and make the midterm exams worth 25% of your grade each, I think is what I do. I don't want to put a lot of more emphasis on quizzes because especially if I'm going to drop 2 of them, I'm not a huge fan. So that's probably what I'll end up doing is the final exam will probably be worth 30% and the regular exams will be worth 25% each. So 50% of your grade will be in the midterms and 30% will be in the final. How about 3C? Yeah, sure. Here's where I feel like an idiot, where it's something that I didn't tell you how to do. It says, okay, mark each true or false. So it says, let's see. It says, if x is an eigenvector of an invertible matrix, then negative x is also an eigenvector of A inverse. Well, that's a really good question. So, why is that? So, um, any guesses? So, I think the answer is false here. So, let's suppose if x is an eigenvector, we'll just write e vector of a, right? What does that mean? It means that a times x. Oh, you know what? The answer is actually true, I believe. It means a times x equals lambda x for lambda in the real numbers. Okay? So, what do you do here? Multiply both sides of this equation. If a is invertible, right, then multiply both sides by a inverse. And if you do that, what do you get? Well, on the left-hand side, you get the identity matrix, so you just basically get I times x, but that's just x. And on the right-hand side, you get a inverse times lambda x, so you can just, the lambda is a scalar, so just pull it out, and you get a inverse times x. Well, now just divide both sides by lambda, and you can do that, right? You can't divide both sides by a number unless you know it's not 0. But lambda is not 0 since a is invertible, right? So we know one of the sort of statements we added to the invertible matrix theorem is that if a is invertible, that's equivalent to saying 0, sorry, 0 is not an eigenvalue. Okay, so if the matrix is invertible, that lambda can't be 0. And so what this tells me then, if I just rewrite this a little bit, we get a inverse x equals 1 over lambda x. And so what did we prove here? Well, we proved that if x was an eigenvector of a, x must also be an eigenvector of a inverse, right? Because I have a inverse times x equals a scalar 1 over lambda times x. So it turns out all of the eigenvalues of a inverse are just the reciprocals of the eigenvalues of a. Now, here's the thing. This question, though, the answer is actually true. Oops, shoot. Rip me. Oh, and okay. Sorry, the answer is true. And the reason why it's true if x is an eigenvector of a, Cx for C not equals 0 is an eigenvector of A, right? So any eigenvector of A, oops, sorry, I'm writing underneath my, let me just do this, I'll move this for you. Sorry, I realize I'm writing underneath my thing there. There you go. Any eigenvector of, if you have an eigenvector of A, any scalar multiple is an eigenvector of A. Since if you have an eigenvector of A, it's also an eigenvector of A inverse, this means that negative x is an eigenvector so negative x is an eigenvector of A, and that means that negative x is an eigenvector of A inverse. So the negative sign isn't really special in terms of being an eigenvector of A inverse. It's just that any scalar multiple, any eigenvector of A is an eigenvector of A inverse, and any scalar multiple of an eigenvector is also an eigenvector, except for 0. Hopefully that answers your question. So if you have any follow-up questions, so I have to, again, if you're coming in late, there's going to be a little bit of latency on this stream. It's going to be kind of 20 seconds behind, 25 seconds behind, I don't know. So if you want to follow up about 3C, mention it in the chat. Maybe even can you write 3C in there so I know that you're referencing that problem. Anyway, can I explain the last question on quiz 7? Bunny, I'm actually sorry. You'd have to copy and paste it into chat. I actually don't know what it is. Let me see if I can look really fast here, actually. I think I can actually check Canvas. Never mind. I don't know why I wouldn't be able to find out, so let me double check here. The last question. Why are there so many? Why are those questions blank? Okay, so I don't know if you mean, so I don't know, I see two blank questions. I don't know what the deal with that is. So if you're referring to question 10 on the quiz, I don't see any question there, so I don't know what the deal with that is. But for question 8, which is the last question I can see, so maybe if you mean that one, it says if a matrix A is similar to a diagonal matrix D, whose diagonal entries are 2, 3, and 4, find all eigenvalues of A minus I. Please order your answers from small. Dude, this is not. Sorry, I'm just looking at the problems here. A minus I squared. Okay. Question 8. Okay. All right. I need to add a new slide here. So this slide's going bye-bye. So you have about 5 seconds to take a picture of the screen. Oh, I see. It had. Okay, you're supposed to do it in those three. He should have put. This is your. Okay. Zhejiang. All right. Sorry. Anyway. Here. Sorry. You have 5 seconds to take a picture of this. 1, 2, 3, 4, 5. All right. Trying to take a picture of me though. All right. All right. So let's see. So A is similar to a diagonal matrix A whose diagonal entries are 2, 3, and 4. Find all of the eigenvalues of A minus I. Okay. Well, okay. So A has eigenvalues. A has eigenvalues 2, 3, and 4. Right? Because obviously if A is similar to a diagonal matrix with those diagonal entries, those have to be the eigenvalues. Find the eigenvalues of A minus I. So if you have A minus I, let's just do this, times, let's suppose that, doesn't say 3 by 3. Okay, let's just say that X is an eigenvector. Let's just say X is in the eigenspace of 2. And let's say we do A minus I times X. Then we get AX minus IX like that. And that has to be 2X minus X. Subtract I from each of the diagonal entries and then square those diagonal entries. Yeah, let me see if we can do this a different way. Maybe you're right here. Sorry, I have not. This problem is a little out of left field for me. I was not thinking of this. I don't know. Let me see. So subtract I from each of the diagonal entries. Okay, so so if A is similar to a diagonal matrix, you can write as A is PDP inverse, right? So if we multiply, how does that go? Sorry. Let me check my slides really fast. Something's bothering me. My brain's not working right now. Sorry, you guys. You're saying don't subtract 1 from each of the diagonal entries and square those. So I think that's right. So I think the eigenvalues, so it should have been that the eigenvalues are 1, 2, and the eigenvalues of a minus I are 1, 2, and 3. And so, yeah, I believe that's correct. Let me, smallest to largest, 1, 2, and 3. Okay. Oh, sorry, not 1, 2, and 3. 1, 4. Yes. So you're exactly right. Sorry. The way you can do this problem, the last problem of the quiz, is if you, yeah, so if you subtract I from it, it's just going to subtract 1 from each of the eigenvalues. So like I said before, I was starting to work on it just to kind of demonstrate why that was the case. If you do a minus I times x, where, I don't know why I'm using red here. Let's just say x is an eigenvector with value lambda. Then I minus x, you get ax minus ix, and that would just be lambda x minus x, so that gives you lambda minus 1 x, right? So that means that if lambda is an eigenvalue of a, lambda minus 1 is an eigenvalue of a minus I. And then if I just called, so in this problem, right, if we call a minus I, if I call that just b, b equals p dp inverse, where d has diagonal entries 1, 2, and 3, right? So b squared would be equal to just, it would be equal to p dp inverse times p dp inverse, which of course is just p d squared p inverse. Now, what this says, right, is that b squared, so a minus I squared equals b squared, that is similar to this matrix d squared, right? And since it's similar to that diagonal matrix, which has eigenvalues, well, d squared is just going to be 1, 4, and 9 on the diagonal entries. Right? Then what that means is that d squared has eigenvalues 1, 4, and 9, and a minus I squared is similar to that diagonal matrix. Well, remember, any two matrices that are similar have the same eigenvalues. So what that means is that a minus I squared will have the same eigenvalues as d squared, which are 1, 4, and 9. So apologies, that took way too long for my brain to wrap around that one. But that's the gist of it. So if you have any further questions on that problem, feel free to let me know. Sorry, I'm going to go back and try to find out. Someone asked me, what is the point of finding if a matrix is diagonalizable? Well, if it's diagonalizable, then that calculation we just did, right, was really easy, because you can see b squared will be equal to p d squared p inverse. And d squared is really easy to calculate because it's a diagonal matrix. So it's easier to do arithmetic with diagonal matrices, and similarity allows us, and diagonalization allows us to kind of work with the diagonal matrix instead of the original one. We don't really do a lot of applications with this stuff in this class, but like for instance, you can take like infinite series of matrices, like power series of matrices, right? You did power series in Math 2B. Well, if you're doing power series, right, you need to take powers of a matrix, and if it's diagonalizable, it's really straightforward to do that. basically. So like for instance, you can actually do e to the matrix x, e to the x, where x is actually a matrix. And to do that, you have to do it via power series. So that's kind of the reason you're not going to see it in this class. You will see it in Math 3D though. Take Math 3D, you'll get to see that. Anyway, number 6. I'm assuming you mean on the quiz. So assuming you mean number 6 on the quiz, it says if a 4x4 matrix A is singular and similar to a diagonal matrix D, which are the possible diagonal entries of D? So just remember that if a matrix is singular, singular means not invertible. Okay, singular means not invertible. So if it's not invertible, 0 has to be an eigenvalue. So for question 6, there was only one choice where 0 was an eigenvalue, and so 0, it has to be the choice in number 6. It has to be the choice that has 0 because the matrix is not invertible. I'm sorry, I don't understand that question. Does it mean what happens to A? What will happen to lambda? Yeah, no problem, Matt. It's like I said, it's pretty straightforward. It's just that you got to remember that determinant equal to 0 and eigenvalue of 0 and an eigenvalue of 0, those are now equivalent to a matrix being not invertible. So if it's invertible, its determinant has to be non-zero and it has no 0 eigenvalues. Yeah, no problem. It's kind of tricky. Yeah, singular is not invertible. It's weird. Basically, you can think of sort of like a singular solution to the homogeneous equation as being like a non-trivial solution. If you have a singularity, that would be like a non-trivial solution to ax equals 0, which of course you only have if the matrix is not invertible. So we had a question in chat. I said, I don't know what it means. Does it mean what happened to A, what will happen to lambda? I'm afraid I don't understand the question. So maybe if you can rephrase that a little bit. Let me just mention again, if you haven't done it yet, please go do the scanning assignment. You will get 4 bonus points on the final, okay? 4 points on the final. If the final is worth 100 points, it's 4%. It's not a lot, but if the final is worth 60 points, well, the midterms were 70, so it probably worth closer to 70, but it's 4 points. 4 points is 4 points. It won't be more than 100 points, so it'll be at least 4%, might be more. Can you explain the question 25 in exercise 5.3? Can the zero vector be an eigenspace? So no. It can be in an eigenspace, but an eigenspace can't be the trivial subspace, right? So let me go back and read that question just to make sure it's asking what I think it's asking. Exercise, let's see, so exercise 25, it says A is a, am I in the right section? Bunny, I'd prefer if you used white paper. I guess it could be lined. There's no real reason why it couldn't be lined. The biggest thing about lined paper is it's usually not the right size. And I'd like it to be the right size just so it matches the output of the exam. So that's sort of the real reason to use like 8.5 by 11 paper. If it has lines, it's not a big deal, but usually most people's notebook paper is not 8.5 by 11. I don't know. You know what? If you haven't done it, you could even resubmit. If you've already done the practice scanning assignment, just try doing it on lined paper. If I can read it, I'll give you the points for it. And, that makes my life easier, so give it a try. Just to see how it goes. Okay, so problem 25 in section 5.3. A is a 4x4 matrix with 3 eigenvalues. One eigenspace is one-dimensional, and one of the other eigenspaces is two-dimensional. Is it possible that it's not diagonalizable? Okay. Okay, this problem says the A is 4 by 4 with 3 eigenvalues. Now when it says 3, I'm assuming it means 3 distinct eigenvalues. And it says, let's just say we have lambda 1, lambda 2, and lambda 3. So it says, let's assume that those are all different, because otherwise this question can't necessarily be answered. One eigenspace is one-dimensional. So let's say this one has the one-dimensional eigenspace. Lambda says one of the other eigenspaces is two-dimensional. So let's just say that's lambda 2. And it asks, is it possible that A is not diagonalizable? So here's the thing. Lambda 3 has to have at least 1. Okay? If you have an eigenvalue, it has to have an eigenvector. The 0 vector by itself cannot be an eigenvector, right? So the eigenspaces always have to be at least one-dimensional. So what that means is that the answer to this question is no, A has to be diagonalizable because, remember, we have that big, long theorem in section, I think it was in this section, 5.3. Basically, if all of the eigenspaces add up to the number of like rows or columns, since we only talk about square matrices being diagonalizable, so if these guys add up to 4, then it will automatically be diagonalizable. So the thing is if you know that one of the eigenvalues has a two-dimensional eigenspace, you're done. The only way it could be one-dimensional is if all 3 of them were one-dimensional. Okay? Does that answer your question? So, but yeah, the 0 vector can't be an eigenspace because to be an eigenvector, you have to be non-zero, right? That's actually go back and look up the definition of eigenvector. Eigenvectors have to be non-zero. So what that means is that to have an eigenspace, you have at least one non-zero vector in that eigenspace, which means you have a lot of them, since any scalar multiple would also work as well. Okay, but yeah, any eigenspace has to be one-dimensional at the minimum. All right. Other questions? I'm gonna pause for a moment and just get a glass of water real quick. All right, I'm back. All right. Can I explain number 25 from 6.1? Yeah, probably. Let's see. Okay, so all right, so from, sorry, my hands are slightly wet. So from, let's see, number 25 in 6.1, it says if V equals, say, AB, describe all vectors xy orthogonal to V. So it says hint, consider V equals 0 and V equals not equal to 0, sorry. So obviously, if V is the 0 vector, so if A and B are both 0, then obviously x, y, all of the vectors orthogonal would just be, all of the vectors orthogonal to that would just be R2, right? If V is a 0 vector, it's orthogonal to everything. So it doesn't matter what x and y are, it would be orthogonal. So let's assume that V is not the 0 vector. So either A is not 0 or B is not 0. So not both of them can't be 0. Okay? So so just take the dot product. So A, B dot x, y equals 0. We want to know for what x and y are going to be orthogonal to V. So if you do that, you get ax plus by equals to 0. And so basically what you get here is, well, let's break it down. So if A is equal to 0, okay, so if A is equal to 0, then it's all vectors x, y with y equal to 0. If B equals 0, it's all vectors x, y with, oh sorry, I forgot what I'm writing here. It's going to take getting used to. With x equal to 0. There you go. Okay. And if x and y are both, if A and B are both not equal to 0, then it's, I don't know, you can just solve for y, I guess, in terms of x. Y would be equal to negative A over B x. So basically, it's any vector that looks like x and any vector that looks like, let me say this, x times 1 and then negative A over B in the second column. So that's what it is. So it's basically that. You have to be careful if A or B are 0, right? But otherwise, if they're both not 0, that's what you should get. Okay? Other questions? We're almost out of time. I will have office hours, so I will shut this stream down at 50 after, or before that if for some reason we do. Although I'll probably leave it up with like the stream's over graphic, but I'll end the stream at 50 after, and then I'll start a new stream at 1 o'clock for the office hours, just because, you know, that way they're labeled separately in my YouTube channel when they're archived, and you can watch them again later. So, other questions? Okay, I'm sad that there only got about 22 people in here, but I guess you can't leave easily if you're in the room, but you can leave very easily, but I'll never know if you're not in the room. The downside of being online. But that being said, you know, please do the scanning assignment. It's very important. Okay, you will get bonus points on the final. All right, please, please, please do the scanning. I want to get as many people. I want to get like basically 100%. I mean, some people have checked out of the class at this point, and that's okay. It happens. You know, at the end of the quarter, I don't expect like every single person to take the final. Most people, a lot of people, some people won't, but you know, there's probably at least 45 of you still checked into this class. If you're in this room and you haven't done it yet, please do the scanning assignment. Okay. Any other questions? Okay, then let me just summarize what I know about the final, and then if you have any more questions, feel free to ask while I'm doing this. So again, it's Monday at 1:30. At 1:30, you will log on to Canvas. I will post an announcement with a link where you can just download a PDF copy of the final. You can, if you want, print it out. You do not need to print it out, but you should note how many pages is it. And I'll give you a tip here. I'm going to do one problem per page just so that everything is very straightforward. So it's going to be a title page and then the number of problems. So if it's 10 problems, there'll be a title page and then 10 more pages. So it'll be 11 pages total. So if it's like 10 problems, get out 11 sheets of paper. On the first sheet, just write, maybe at the top, write math 3A final exam, doesn't really matter. But most importantly, put your name. Try to match up where your name goes with where the box on the title page is. And then maybe go through your other 10 sheets of paper, and on each sheet of paper, write your name. Actually would be a really good idea on each sheet of paper at the top. But write on like one sheet, write problem 1. Then the next one, write problem 2. And then do your work on each one of those pages, okay? When you're done, whether you printed it out or you did it on a blank sheet, if you have a tablet like I do, and you want to, just import the PDF into a note-taking app and write on it directly, as long as you can export it all as a PDF, that's fine too, okay? Whatever you do, you're gonna need to get a PDF copy of your exam. So that means scanning it somehow. See the video I made about how to do it using Dropbox. Dropbox is free. If you go to dropbox.com, it'll say sign up for free. You can get a free account. It's pretty easy. If there's nice features if you pay for it, but you don't need any of them to do this. And then download the app on your phone, watch the video I posted on how to get it into Gradescope, okay? Make sure everything's in the right order, get it into Gradescope. It'll give you a receipt, okay? Check it in Gradescope. Make sure that everything looks right in Gradescope. Yeah, that's a good point, Tharp, that the live stream is recorded. Anyway, check it in Gradescope, make sure everything matches and looks good. And then, that's it. You'll get a receipt that says you submitted it on time, and you'll have 20 minutes. So that means you have 2 hours for the final exam. It's going to go 1:30 to 3:30. You have to have that Gradescope submitted by 3:50. I'll also, by the way, I will make a discussion thread in Canvas. I don't know if I have discussions enabled. I'm going to make a discussion thread. If you have a question, please go on to the discussion thread and ask it. I will check regularly to make sure that I answer all the questions that I can answer in there, okay? Bunny, the class is sort of curved. Basically, the median grade is going to be about a B-. So whatever the median is, if you're above the median, you'll get at least a B-. If you're below the median, you're probably going to get a C+ at best. Maybe there's going to be a little bit of flex there. I'm not promising that exactly, but that's basically how it'll go. That's how the math department wants me to do it, so that's how I do it, okay? That's not me, that's the math department. I just do what they tell me, because certain professors gave out tons of A's and B's in calculus, like way too many, like 50% of his students were getting A's, and he got yelled at by the math department, so I don't want to get yelled at. I'm only going to give out so many A's and B's, okay? So anyway, that's it. So be in front of the computer, or you can use your phone, I guess. You don't really need a computer, but be in front of your computer at 1:30 with an internet connection on 1:30 on Monday. And again, your exam will have to be submitted by 3:50. Okay, 3:50 p.m. I'll check Gradescope, and then basically that's when it's going to stop letting you. I will have an emergency procedure in case for some reason you're having trouble, but otherwise I don't want to deal with 30 of you guys emailing me saying I couldn't do it. So do the practice assignment. Okay? All right, it is time for us to leave. So you can feel free to just jump back in. I'm literally gonna have office hours. I'm probably gonna handle your questions and some of my Math 13 students' questions during office hours. But anyway, I'm gonna leave this stream over thing up for a minute. But thanks for coming, guys. I'm glad that you came. If you haven't subscribed to my stream, please just subscribe. If you haven't subscribed, just subscribe, and you can unsubscribe like maybe in like a month. I don't really care. Obviously, when you're done with the class, you don't need it, but it'd be really handy because if I get 100 subscribers, I'll get a nice URL instead of the garbage URL that I currently have that I post in links. I want like youtube.com/Dr. Northrup or whatever. That'd be really nice. So you can subscribe. Just do me a favor. All right. Anyway, have a good one, guys. We'll see you in office hours if you choose to come in. I'm going to shut the stream down in about a couple minutes, but I'll leave the stream over graphic up here.